Our discussion today is going to be centered around logarithms. So just have a quick look at this learning goal. Right? I'll define logarithms as indices. Okay, this means that a to the power of x equaling b is the same thing as x equals log with a base of a of b. And so we're really going to dive into that. Here we'll start off with some log laws. Okay, this is what logarithms are, or the log laws are. Okay, it's worth pausing, writing them down. All right, so in order to do that, what we need to do is we need to have a look at exponents and logarithms, because essentially what logarithms are is that they are the opposite or the inverse of exponents. And so hopefully at this point we're pretty comfortable with exponents, that's indices, powers, and we're going to relate it with logarithms. So I'm just going to pick a base number, because we saw with logarithms that had a base. I'm just going to pick the number 2, and I could write down the number 2. And with how exponents work, it's just a lot of multiplication. So I'm just going to go 2, 4. We know that's equal to, okay, well, 2 is equal to 2 to the power of 1. Same thing with 4. We say, yeah, 4, that's 2 to the power of 2. And with 8, that's 2 to the power of 3. Okay, and so we can kind of see that pattern there with exponents. That's nothing new, and it also works if we keep going up the way. So if we, instead of multiplying by 2 to keep going down, we can divide by 2 to keep going up. So we get 1, and then a half, and then a quarter. Okay, we know these, that's just going to be 2 to the power of 0. This one's 2 to the power of -1, and this one's 2 to the power of -2. Okay, hopefully we're kind of getting a bit strong with our indices, and that's no concerns for us. Okay, now we're introducing logarithms, and so in order to explain this, I'm going to have a look at the powers of those exponents. So I'm just going to write those ones down. Okay, so I've got -2, -1, 0, 1, 2, 3, 4, 5. And I'm going to explain how the logarithms work. Okay, so with logarithms, we'd say that, well, it's equal to the log, and our base number here that we chose was 2, so it's a log base 2. And now I just want you to scan your eyes over this one, except this one here. And I'd say that that is going to be a quarter. So if I've got log with a base of 2 equals a quarter, okay, that would equal -2. If I had a log with a base of 2 being a half, that would be equal to -1. If I had a log with a base of 2, that would equal of 1, that would equal 0. If I had a log with a base of 2 of 2, I'd get it equal to 1. Okay, but logs really help us answer the question of how much of a power is needed. So these are all nice because they are exact indices. But if we were posed with the question, well, 2 to the power of what is equal to 7? Okay, and so there's not an exact integer value that you can take the power of. It's a question mark there. But intuitively you could go, yeah, well, we know that 2 to the power of 2 is equal to 4, and 2 to the power of 3 is equal to 8. So I know that that question mark is in between 2 and 3. Okay, but if we want to get an exact value, what we do is we just say, well, if our base number is 2 of 7, that's going to give me what the power is. And this is the powerful thing with logarithms. Okay, just to explain a few of the log laws. Okay, this is the 5 of them. So you can see the 4th log law here is that if you've got the base being the same as the number inside the logarithm, okay, it's going to equal 1. Okay, and intuitively that makes sense, because essentially what it's saying is 2 to the power of what is 2. Okay, that's how we read the logarithm, and we'd say that, well, 2 to the power of 1 equals 2. So that gives us log law number 4. Okay, similar thing, we can see it with the one above. Right, how we are reading these logarithms off is we say log with that base of 2 what power do I need to raise it to get 1? Okay, the thing of the log. And we'd say, well, 2 to the power of 0 is equal to 1. So that's kind of why these ones work here. That's log law number 5. Okay, and so you could just do a little bit of deduction here. So have a look at log law number 3. Okay, we know that 3 is equal to log base 2 of 8. But what we can do is we can say, well, 8 is actually just 2 to the power of 3. Okay, and bringing that down, we'd say that, well, that's 3 times log of 2, which is just equal to 3. Okay, so this is, and you could do a similar thing for log law number 1 and log law number 2. It's also useful to consider tables of values to see the relationship between logs. So if we just took this rule, y equals 2 to the power of x, and we can fill this in. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, to the power of 2 is 4, and we could just fill this in here. Okay, we saw that above. This relates with, and hopefully shows the equivalence of the inverse with logs. So if we take x being equal to 0 in this case for this rule here, okay, that means 0 is equal to log base 2 of what? Okay, and so another way to reframe the question, right? Because we know of this equivalence, and it's so important, I want you to put a big box around it. If you've got a to the power of x being equal to b, the equivalence of this, and it goes both ways, is that you can take log of that base a of b being equal to x. So another way to think of it or reframe it is that you say, well, 2, which is my base number here, 2 to the power of 0, this one here, equals what? You can say, well, 2 to the power of 0 is 1. I'll do that in blue. Is 1. And then you can consider it x being equal to 1. 1 is equal to log base 2 of what? Okay, and so then you ask yourself the same question. Well, 2 to the power of 1 is equal to what? Well, 2 to the power of 1 is 2. Consider it for x being equal to 2. Again, you just go, well, 2 to the power of 2 is equal to 4. And we can see, if we keep doing that for x being 3, x being 4, x being 5, we have some equivalence here. So this is our log and exponent equivalent. Referring it back to the learning goal. Okay, I will define logarithms as indices. They are just inverses. So this means that a to the power of x is the same as log base of a of b is equal to x. Okay, these two are equivalent. Don't want to understate how crucial it is to get this understanding right. Alright, once we've got that business out of the way, then we can just go ahead and simplify some logarithmic expressions, okay, or evaluate them. So if I look at this, well, log base 5 of 125, and I want to evaluate it, what I need to do is I need to just set it equal to something. Okay, and so well, what this really means, if we remember that log base a of b equals x has equivalence with a to the power of x equals b. So the way to reframe the question would be to say 5 to the power of x equals 125. Okay, going from this step here to this step here, that is the equivalence statement. Once you're here, well, 5 to the power of x, that's equal to 5 to the power of 3, that's what 125 is. So then you say x equals 3, right? Therefore, log base 5 of 125 equals 3. Example 2 here, simplify the logarithmic expression and evaluate where possible. Well, we can see we've got a few terms being added and subtracted, and it's important to note that all of the base terms are the exact same, so you can apply those log laws. Alright, here we're going to use the first log law to simplify this one here. We've got log with a base of 4 of 6 plus log with a base of 4 of 9. What we do is we multiply those terms. Okay, and then we're still just going to subtract off that log base 4 of 3. Okay, when we evaluate that, so we got log base 4 of 63, subtract log base 4 of 3, we go ahead and apply the second log law, which tells us that we need to do division because we've got the subtraction of the two logs, and that gives us log base 4 of 21. And it says evaluate where possible, so we kind of make this deduction, x equals log base 4 of 21, and essentially what the question is here is 4 to the power of what equals 21, and there's no nice integer solution, so we are just going to leave it as an exact value. Okay, again, we need to simplify this and evaluate it where possible. Here we're going to have to use a few more log laws. Simplify this one. I see that I've got the 2 floating in front here. I don't really want it there, so I'm going to use the opposite of the third log law, which just tells me that that 2 originally belonged up in the power. Okay, subtract again this one. Alright, that 4 out the front originally belonged up on top of that 4. Okay, that is the opposite of the third log law. Then we can simplify this out a little bit. Log base 3 of 144, subtract log base 3 of 16. And then we can go through, we can evaluate this. Log base 3, 144 divided by 16. Okay, super important to note that all of these bases have been the same. That's why we can apply these log laws. They have to be the same. And then we've got 144 divided by 16. It's going to give us 9. And then evaluate where possible. Well, we can do that in this case. X is equal to log base 3 of 9. What this is more or less telling me is 3 to the power of what equals 9. I know that x is equal to 2. So this guy here just equal to 2.